Yeah, I worked at TypeSafe for 2 years doing consulting and training around Scala and Akka. And then I spent 2 years as a sales engineer at DataStax, focusing on Cassandra and the DataStax platform. So today I wanted to talk about Akka distributed data. To kind of give a background, I'm going to start with kind of what the challenges of distributed systems are, what the problems we're trying to solve are. I'm going to give an overview of CRDTs. Talk a little bit about Akka and Akka clustering, just a really brief overview if you haven't heard of Akka, and then go into Akka distributed data. So let's talk about the challenges of distributed systems to start with, to give you some of the challenges that we're trying to solve. A lot of people have probably heard of the fallacies of distributed computing. There's a lot of discussion out there about CAP theorem and all the problems of replicated databases. What the fundamental problem is that whenever you have two servers communicating over a network, there's always going to be a delay between those two servers, right? Replication is always going to be slow between the two servers. When I have a cluster of servers, a server will always fail. A server will get out of sync, and it will, and so its view of the world will become out of sync with the other servers, right? The network is not reliable. Right? Our latency is always going to be greater than 0. We always have this limitation of the speed of light for replicating data. And we also have a limited bandwidth, right? There's a limited amount of data we can send over the network, right? So when we're doing distributed computing, we're running into these challenges of how we replicate the data across the network effectively, and how we can keep a somewhat synchronized view of the world. So the traditional approach to doing this was using something like total global ordering, right? So, the idea that I would do something like lock my entire, every node of my cluster and update all the values synchronously. Try to do these global distributed locks. Well, that doesn't work, right? If I have more than, 2 servers, I put a lock on, more than 2 servers, and I'm also having to lock 5, 10 servers. That gets really slow. It's very hard to synchronize across a large cluster of servers. It doesn't scale, and it causes a lot of performance problems. So right now, then if you start to think about this, well, if there's no way to really lock my data globally and get a single synchronous view of my data, then my data is really not the single opaque value. It's not just a simple type. I can't have a fixed, bank account balance or, a score. It's hard to get just a single view of my data. The other thing I really can't do is I can't do asset transactions, right? I can't do what's, in the relational world, everyone's used to doing, an asset transaction. It's a consistent view of that data, and that's just not possible when I get into a distributed data model. If anything you get out of this talk, I want you to remember this. This is what happens when you do global locks with a distributed system, right? You get basically this huge backlog whenever you try to do global locks, distributed transactions. You get a really slow performance, and it doesn't scale because you're trying to, have a single point of synchronization for your entire system. You've all probably heard of the CAP theorem. What we're going to talk about today is building a system that really focuses on being eventually consistent based on the CAP theorem. So it's really focusing on being highly available and partition tolerant. So when we talk about the CAP theorem, consistency is the consistency of the data. So, what is my view of that data? Do I have a strong consistency? So the idea with the CAP theorem is that, right, there's the original paper on the CAP theorem that said I had to be a fixed point between consistency, availability, and partition tolerance. Then there's a CAP theorem update, or what was it, 2.0, where they said, really, you could think of this as more of I can kind of choose the point in this Venn diagram of where I want to be depending on, my different transactions. And so I can kind of, adjust my consistency levels. So if I want to, adjust from being, instead of having a eventual consistency and completely giving up availability, I can kind of tune my system so I can have a stronger consistency level by decreasing availability. So really, we want to talk about today is how we kind of can tune this where we end up in the CAP theorem. So when we talk about eventual consistency, what does this mean? Really, what it means is embracing failure in distributed systems. We know we can't get an exact, consistent view of our data. Strong consistency is not possible. There's no way of doing that. So we're going to embrace the failure and say, you know what, we are going to have eventual consistency across our global cluster. So how do we reconcile this? How do we deal with this differing views of the data? So how are we going to, if we see, different order of operations coming in, if the transactions on our data are differing and causing different views of this data, how are we going to reconcile all of these differences? And when you talk about eventual consistency, there's two ways of basically looking at eventual consistency. One is probabilistic guarantees. So that means that I'm probably going to get the same view of the data, but I might not. So if you're familiar with Dynamo has a probabilistic guarantee. What that means is that it won't always return the exact ordering of operations on the data. So I might get slightly different views of my data because it's a probabilistic guarantee on how it resolves the conflicts. The other view of eventual consistency is with strong guarantees. That means that the order of operations are always going to be exactly the same. So that means that when I do resolve the conflicts of my data converges together, I'm guaranteed to get the same view no matter how I look at it. So what we want to do today is we want to move towards a strong consistency model to get an exact view of that data. So as a background for Akka distributed data, we're going to first talk about what's called CRDTs. They're conflict-free replicated data types. There's been a lot of academic work around CRDTs. There's a number of papers about CRDTs out there. It's a fairly new area that's being researched of how I can build conflict, data that doesn't have conflicts in it. And the fundamental idea behind it is I want to avoid conflicts. I want to avoid fights between my data. I want a way to be able to resolve the differences in the views of my data. So there's a lot of different definitions about CRDTs. One I really like was this. They're data types that can guarantee convergence to the same value in spite of network delays, partitions, and message reordering. So no matter what order of the operations come in, if I have a split brain in my network for a small period of time, and then that network comes back together. And so, maybe, I get, messages coming into one part of my network while the other part of the network is down. How can I resolve those? So I always converge to the same, value in my data. When we talk about CRDTs, if you read the original CRDT paper, it talks about there's state-based and operation-based CRDTs. So CRDTs is, convergent or commutative. So really what we're focused on today is more of the state-based CRDTs. So what the CRDT is, it really rethinks how we view the data. So instead of thinking of the data as this single consistent value, right, instead of a place to just dump our values, we want to really kind of abstract out the data type and really think about more of the structure that tells us how to build these values. So instead of something simple as a counter with a fixed value that I'm having to synchronously update all the time, I basically want to figure out how I can calculate that counter. So how I can derive the value of the counter. So why CRDTs? And what is the value of this? The beauty of CRDTs is that I can replicate data across the network without any synchronization mechanism. So I don't have to do any distributed locking, no two-phase commits. I don't have to lock my database and do an update and then unlock it. I don't have to have a global coordinator, a master-slave architecture, any of this. What I can do is just replicate the data, and it'll eventually reach a convergent state. So another way of thinking about CRDTs is consistency without consensus. So I don't have to have consensus from all the nodes to reach a consistent value. To talk about So what's some of the other values of CRDTs? One of the big things they do is you can sacrifice linearizability, guaranteed ordering, while still remaining correct. What that means is, like, going back to the counter example, I can do a count, and I can get the order of my counts in a different order and still arrive at the same final value. So I don't have to guarantee the ordering of the operations in my system to arrive at the correct value. And where the CRDTs become extremely valuable is if I want to build, in the CAP theorem, architectures that are, highly on the AP side of things, highly available, highly partition tolerant. So this is a perfect data type for cloud computing. Cloud computing, I have a lot of, the servers are not reliable. I can have network partitions, down data centers, down servers. There's not a lot of guarantees in my cloud computing. And so what I want to do is I want to move completely away from having to depend on strong consistency and move into the availability of the partition tolerant side of the world. So how do we build CRDTs? What are some of the fundamental building blocks around CRDTs? One of them is monotonic sequences. So a monotonic simply means that I'm always going in one direction. So it's something like a counter, right? So if I have a monotonic counter of, say, like a score for a game, I know that score always has to increase. And because it's always increasing, it's always in a monotonic line, and if increasing, I know that I can never be decreasing. And what that means is that the order of operations doesn't matter, because I know that, regardless of the ordering, I'm always going to be increasing, right? So I can have a sequence that always increases or a sequence that always decreases, one direction or the other. And what's nice about monotonic sequences is I don't have to have any coordination. So I can receive something like a count or an increase to that monotonic sequence without any external coordination. So monotonic sequences are one of the fundamental building blocks of CRDTs. Some of the other basic building blocks of CRDTs that are used are, going back to our basic math. These are convergent operations, right? So if we look at addition, right, addition is associative, meaning the grouping doesn't matter, right? No matter what order of my additional operations, however they come in, right, I'm going to get to the same answer no matter what, right? So if I do A plus B plus C or A plus B plus C, it's the same thing. The other nice thing is a commutative property, right? It doesn't matter if I do A plus B or B plus A, that ordering of operation doesn't matter. And idempotent, right? Duplication doesn't matter. So I can add in, as many A's as possible, right? So if I have an event with like a unique ID, I can, add that event in as many times as I want. And because I have a unique ID, it's only going to, add that event in one time. And so using these type of, basic, mathematical properties, I can build data structures that it doesn't, require an exact global ordering or global locking to get to a final value. Some example operations that are used in CRDTs is, for example, a union of items, right? If I want to union I have a set A, a set B, a set C, right? And I put those, the first time I combine it into a set AB, another set I combine into set BC, another set I combine into set AC. Now I have, 3 different sets. So, how do I arrive at, what is the final set? Well, if I just union all those together, I know that those sets become unique when they finally combine into the ABC. So if you think about this in terms of a global, distributed algorithm, it doesn't matter the order of operations that I've added these elements into the set, I'm always going to converge into a final value of ABC. Another thing is that, getting the max value of an integer, right? The calculation of a max value is always going to arrive at the same, end value, regardless of how I get there. If I'm comparing, 3 and 5, it's always going to do 5. If I compare 3, 5, and 7, it always gives me 7. And using this basic, concept of always arriving at the same max value, I can build data structures around these kinds of concepts. Some examples of the base types of CRDTs. One is a CRDT is a counter, right? A grow-only counter. It only supports increments. So what that means is I could use this for, something like likes on my Facebook page, or, voting on like, Reddit things like that, or, counting something that doesn't have to have an exact value at an exact point of time. Instead, I have I might have a slight skew, but I'm always going to be arriving at the final count, with a slight delay. And because that's a grow-only counter, I know that I'm only adding incremental values to it. And then to get, I can combine that grow-only counter into what's called a P&N counter, a positive negative, right? So I can have a counter that, one counts only increments, another for decrements. When I want to see the final value, I can basically take the increments minus the decrements, and I get the final value. The order of those operations doesn't matter, right? I can get as many, votes coming in from all different sides of the system. I can be getting, votes, from one, node A, votes from node B. And it doesn't matter the order they're arriving in, because I'm going to, when they converge together, I'm going to get the total vote will always be the same. Registers. If you're familiar with Cassandra uses last right win registers underneath the covers. So this is what is interesting about CRDTs is the concept of CRDTs have actually been in use for a long time. With like Cassandra and React, CRDTs has really kind of formalized these data types into a more formal, structured so that they can be more broadly used. But the general idea behind CRDTs have actually been in use for a long time. So like with Cassandra, last right wins, what that basically means is if I have a write to a column, two conflicting writes, I'm going to basically just look at the timestamp and see which is the latest timestamp, and the latest timestamp wins. So it's a way of resolving those conflicts and knowing what the final value is going to be. In React, what React does is it's a multi-value register. It basically says, let the business decide, right? I'm going to store both of those values and let it decide. CRDT sets. These are grow-only sets, right? So that means that I can only add items to my set. I can never remove. And then when those sets are, merged across nodes, basically the union of items. So it's a type of set that I can't remove from. And then what I can do is I can build on a grow-only set to build what's called an OR set, an observe-remove set. Right, so just like I have a monotonically, increasing counter and a monotonically decreasing counter, I can do the same thing with my sets. I can have a set that's only observes that things have been added, another set that's only observed what's been removed, and then I can keep track of what is the final state of my set. Internally, for the actual implementation, they use something like version vectors and birth thoughts. To arrive to a final, convergent value. What's interesting about OR sets is once removed, an element cannot be re-added. So that's one way that I'm, resolving these conflicts in this distributed system. There's CRDT maps, similar to sets, right? Observe remove map, observe remove multi-map, last right win maps. Positive negative counter maps, so these same kind of concepts of basically figuring out how to resolve conflicting values as they come into the map and what values win. One of the most powerful concepts around CRDTs is that CRDTs compose. This is what's really interesting about a CRDT, is that a CRDT value can contain another CRDT. So I have something like an observe remove set. Well, that observe remove set could actually contain a grow-only counter. And so because these CRDTs compose, I can basically have nested CRDT data types, and compose those data types together. So not only does the top level data type converge, my nested values within that data type converge. And so I can compose these and make really interesting structures out of them. So like I could do an observe remove map with a last right wins register inside of it. So that way I know if I have a map with the counters or with the register values, and I want to figure out I can converge that map, and then inside those values I have conflicting values, and I can resolve those with last right wins. There's a number of CRDT implementations out there. React has implemented, React has a convergent replicated data types inside of the React database. SoundCloud had built their own CRDT implementation called Roshi. SoundCloud actually uses CRDTs quite extensively. If you think about a lot of like what SoundCloud does is, like the number of views for a song, or the number of likes on a song. These kinds of values are not something that has to be, at an exact moment of time, the number of likes on my song. What I want is, an approximation of that value. And because I only want an approximation of something like likes or views, right, that's something that can converge to a final value at an eventual point of time. And you can actually do that, something really like a playlist. I can use, a set of songs that converge to if I add, different songs to that set in different locations, and then when I converge those together, I can see, well, those songs have been added, multiple times in different places. Well, that's the same song, so I can converge into a single song set. So that's why SoundCloud is using these data types. And then Akka distributed data, which is the implementation we're going to go into today. If you're not familiar with Akka, I'm just going to give a 5-minute overview of Akka, just a really high-level, quick overview of Akka. How many people have used Akka in here? Most everyone's used Akka, okay. About half the room is familiar with Akka, so we'll make this quick. All right, so Akka is an actor-based toolkit. It's really, they talk about it as a toolkit for concurrency. So that whole idea behind Akka is to make it really simple to handle concurrency and distribution, instead of having to do low-level locking, with mutexes and semaphores, and managing my threads and thread pools. All of this, Akka takes care of all of that for you. Makes concurrency really easy. It has an entire toolkit around error handling and self-healing. It makes it really easy. They talk about the reactive manifesto being resilient. So not only can my systems handle failures, they also can self-heal and, come back online and rebuild themselves. And so they can continue to operate even under failure and error conditions. Akka is also very elastic and decentralized. The idea is that I can handle these type of events that come into my system in a very elastic manner and be scaling. The core of Akka is built around actors. If you've not heard of actors can just be thought of as like this lightweight process. How it works is it's like a walled fortress. It's like this process that I can't interact with directly. I can only send messages into that actor. And because it's this walled fortress, I can never go in and I never change the state manually or update the state manually. Instead, what I'm going to do is I'm going to send the messages into that actor and have that actor managed by the actor system. So it's entirely event-driven. That's what gives Akka its concurrency, is because these actors are managed by the actor system. They're run asynchronously and processed, and they process one message at a time. This gives me a model for sync concurrency, and it isolates out the failure handling, right? So if I'm sending a message into an Akka actor, I don't have to know where the actor lives. It can be, if it dies and gets restarted somewhere else, that doesn't matter. The Akka system can still route those messages to me. Right, so then on top of these actors, so you get a hierarchy of collaborating actors, and that builds out your actor system. So that's the core concept behind Akka, is that I have a hierarchy of actors, and I can send messages down that hierarchy. I can have a parent actor that supervises child actors, and then I can propagate failure up and down the hierarchy. Where Akka, I think, gets really interesting is with Akka clustering. So the idea with Akka clustering is, so I have a system of actors, running on a single server. Now I want to take that actor system, I want to scale it out across a cluster of servers. And the way Akka clustering does that is it doesn't use a master-slave architecture. All right, so like I talked about at the very start, global locking, any kind of distributed transaction, master-slave architectures, that always causes a bottleneck, a single point of failure. What we want to do instead is we wanted to have a peer-to-peer based clustering membership. What that means is that there's no single master in my cluster. There's no one that is the single coordinator for that cluster. Everyone is considered an equal peer in that cluster. That provides really unique architecture because it doesn't matter which, if I lose a server, it doesn't matter which server I lose because it's not the master. I don't have a master, so someone else can just basically take over operations of that node. The cluster communicates via gossip protocol. I'll cover that in just a minute. The other thing, it has like the 5 failure detector, so it can automatically detect when a node is down, right? So if I'm sending messages to a node, I'm not receiving messages back. I can detect that it's using a failure detector to know when to mark a node is not in the cluster anymore. One of the key things for when we get into Akka distributed data is this notion of gossip protocol. So the idea with gossip protocol is that I'm going to share my state by gossiping with my neighbors. So instead of the traditional way of distributed systems was a master-slave, where I have a master who coordinates all the communication out to the slave nodes. So that meant that single point of failure, that single point of communication, and that single bottleneck. The alternative to that is what is called gossiping. And what that basically means is that, and how this works like with Akka Clustering, Cassandra is actually very similar. There's a lot of distributed systems now that do this, is I randomly pick out of the list of nodes available a neighbor to communicate with. So I'm going to randomly pick, node, I'm on node A, I'm going to randomly pick node C, and I'm going to say, all right, this is how I see the state of the world currently. And so you're just randomly, telling your neighbor what this current state of my world is. And that means that I'm not having to disseminate. One node doesn't have to send all the information to all the other nodes. I'm not having I'm not flooding my network with a lot of messages. I'm not having to broadcast the message out. All I'm doing is I'm just randomly picking neighbors and gossiping to those neighbors. And by gossiping, I'm reaching an eventual state of what my cluster looks like. And one of the beauties of this gossip protocol is that it doesn't require a reliable communication channel. So if my network is down, if I have partial network failures, when the network comes back up, all I do is I just continue the gossiping, right? So I'm not depending on a reliable network. What's really, so on top of Akka clustering, so I have this notion of cluster, right? I have a cluster of actors spread across, my servers. Based on this Akka clustering, then I can build a lot of interesting concepts. One is cluster singletons. What that means is that I need to have an actor that's guaranteed to be running on one node. And the way that works is I can listen to cluster membership and guarantee that the cluster, that actor is running on, the oldest node in the network, the cluster. And if that cluster node dies, then I can just guarantee that it gets started on another node. I can do roles, so I can have, say, these group of nodes are dedicated to, my shopping cart. These group of nodes are dedicated to my gaming. So I can dedicate, different nodes to different roles and have them different, tasks assigned to them. I can do cluster events. This is listening for nodes coming up and down, and I can, receive events that, a cluster node has come up or it's gone down and take action on that. I can do cluster-aware routing. I can send messages across that cluster and have it, route the message effectively across my entire cluster. I can do sharding, so based on something like a member ID, I can say, figure out, chunk out how those members get processed. And so what's interesting, I said, people have been using the CRDT concepts for a long time before they're actually formalized. So Akka cluster state is monotonic. So there's the cluster state is a CRDT data type. The Akka team actually came up with this before the CRDTs was formalized. And then, when the CRDT paper was published, they realized, wow, this is exactly what we're doing. We've come up with what is called a monotonic sequence. So if you look at the state of a cluster node, I go to joining. I go from joining to up to leaving, leaving to exit, right? Exiting to removed, removed to down. So if you look at these arrows, this is a DAG, a directed acrylic graph. So I can only go in one direction, right? I can't go from joining to up and then from up back to joining. And I can't go from up to leaving and then leaving back to up. I can only go one direction in this graph. And what that means for something like if we start to look at trying to converge on a monotonic state, a monotonic sequence, if I have two messages, and one message that says this node is up, another message says this node is leaving, well, I know that it's leaving, right? Because I know that I have to have gone forward in that state. I know I couldn't have gone from leaving back to up. I can only go forward. So I know because it's a monotonic sequence, I'm at the farthest point in that state. So if I see, conflicting values of, up versus leaving, I always know how to resolve those values. And so that's what makes Akka Clustering be able to, scale and coordinate between nodes without having any kind of central locking mechanism, is because I can resolve conflicts without having to have that central locking point. All right, let's talk a little bit about Akka distributed data. So on top of Akka, the core Akka, it's built a kind of a replicated in-memory data store. The idea is that I basically store the data in my Akka actors, and then I replicate it out to other nodes in that cluster. I want to share the data between those cluster nodes so they can, get a view of the data. And the idea is to be able to build a very low latency and high availability distributed data, like a caching layer almost in my application tier. And I also want to make the API very easy to use, a key value store like API. So I don't want to have to make it so, I have to deal with a lot of low-level APIs. I want to make this very easy to, add and remove something as simple as keys. Akka distributed data uses the state-based CRDTs. So I mentioned CRDTs, they're state-based and operation-based. It uses the state-based CRDTs. The slight downside of a state-based CRDT is they require storage of extra data to facilitate merging. So they are maintaining a lot the state information so they can make it easy to merge the data and come to those values. So I do have a little bit more overhead in terms of storage and network communication. The original state-based CRDTs in Akka distributed data required the entire state to be disseminated. Right, with Akka 2.5, they introduced delta state CRDTs. What this does is it allows only the recently applied mutations to the state to be disseminated. So this really saves on network overhead, so I can basically detect the differences in state between and what's changed and only replicate those. So what makes the Akka distributed data so powerful is the data resolution mechanism. So what happens is, I have a cluster of nodes, and I want to disseminate that information across that cluster of nodes. What I can do is I can do basically a concurrent update across all of those nodes, and not worry about trying to lock or force a locking mechanism on them. Instead, I can use these monotonic type of merge functions to merge my data. So basically, I can broadcast the data out, and the individual nodes can merge the data into a convergent value. And I can also have a fine-grained control of consistency levels of my reads and writes. I'll talk about that in a minute. What else is nice is because Akka is based on a peer-to-peer cluster, I can update from any node without coordination. So I'm never having to go to a central node for coordination. I'm never having to do any kind of distributed locking mechanism. When I talked about fine-grained control of consistency, what this means is I control the number of nodes that data needs to be read from or written from. So I can say write local, so I'm going to just write the data to the local node first. I can say I want to write it to 3 nodes. I want to write it to the majority of my cluster. I want to write it to all. So I'm controlling the number of nodes that I'm writing to, and that's allowing me to tune the consistency. So when I say write majority, that's the number of nodes in my cluster divided by 2 plus 1. Right, so if I have 10 nodes, I want to write, that means the majority will be 6 nodes. And what I can do is I can actually tune the consistency between the reads and the writes to optimize for the read side or optimize for the write side. And the way I do that is if the number of nodes written to plus the number of nodes read from is greater than the number of nodes in my cluster, that means I'm going to see a consistent value. So again, if I have 10 nodes, I could write to say if I want to make writes extremely fast, I could do a write local, but then I could do a read from all. So I could do if I have a fairly high level of trust in my my network communication, I could do write local. Just be sure that the write's done locally, and then read from majority. So that's going to make my writes faster than my reads. So that's allowing me to tune my consistency level. I'm getting stronger consistency levels by tuning the balance between the reads and the writes. So the way the data is distributed, so going back to this, so I say write, local, write to, so I'm saying how many nodes do I need to write to or read from. So the way that that data gets distributed is, depends on the consistency level. So when I say write local, it's going to just write to the local node and then asynchronously, using gossip, disseminate that out to the remaining nodes in the background. If I say, write to n, that'll actually force the direct replication out to n nodes. Write to majority will force a replication out to n nodes. So the way the data gets distributed is affected by those consistency levels that I'm marking there. So I'm saying in that consistency level, I'm controlling how the data is being disseminated across the network. And then what happens in the background is, after I've written it to say, 2 nodes and I have a 10-node cluster, gossip is going to be used to disseminate the rest of that information. So it'll be just put onto that the gossip protocol and spread across the network. Akka distributed data currently has, it only supports some of the CRDTs that are available today. They all implement the replicated data trait. So they have a monotonic merge function. Right, so this is a common data trait with a common merge function that basically tells me how I'm going to merge my values. What's supported today is grow-only counters, positive-negative counters, grow-only sets, observe-remove sets, maps, registers. What I mentioned before is powerful about these data types is that they can compose. All right, so I can have an observe-remove map with a PN counter. So I can use these CRDT or these base data types to compose more complex data types. So I could have like a grow-only set with a last write wins register. And so I can compose these together to make more complex types. And what that means is that when Akka distributed data sees the values, it can it can merge those values inside of the data types as well. So I can merge it multiple levels. And I can compose the merging functions. So I was going to show this in both Scala and Java, just kind of give you a really high-level glimpse of of what the Akka distributed data looks like. The base data type in Scala is this replicated data, right? So I'm basically saying it's a type T is of type of replicated data, and the only thing the replicated data has to do is it has to support a merge function. So that's the only thing that I need to do to implement a replicated data type is to be able to support a merge and say how I do that merge. So as an example of in Java is the two-phase set. I've trimmed out a lot of the code here just to give the primary parts of it. But what a two-phase set is basically I have the set of adds and the set of removals. And when I merge that data, I'm basically taking all the adds and all the removals and converging those together into a final state. So I'm getting the final set of data based on that convergence. The way Akka distributed data works underneath the covers is it uses a Replicator Actor. So every node that participates in my Akka distributed data cluster, let me back up. So in my cluster, I can specify a specific role. So I can say these nodes in my cluster are distributed data nodes. And all those nodes will have a replication actor. And that replication actor communicates with the other nodes in the cluster to replicate the data. This replicator can be thought of as like a local key value store, where the keys are the strings and the values are the replicated data. And so what the replication actors do is they can either communicate with each other directly, like if I do a write to n, or they communicate via the gossip protocol. And so all operations is done through my local replication actor. So I'm going to communicate that replication actor. I don't have to worry about disseminating the information myself. So it's basically like I'm dealing with a local data cache, and then it's going to automatically be updated across the network for me. Akka makes it really easy to get the local replicator. I just do a distributed data based on the actor system. I ask for the replicator. And then once I get a handle on that replicator on my local node, I'm going to use that for all my local communication. I can do things such as get, subscribe, update, delete. So I'm going to basically subscribe to a topic or a key. I can get notifications that new values have come in for this type. So everything is happening through this local replicator. Update, what I basically do is I create an update message that's keyed on the distributed data type. I set the initial value, the write consistency, and then my request context. And then I basically send the replicator this update message, and it's going to update my local cache and then disseminate that update across the network. As an example of an update, right? So this is an example of an update message, right? I'm passing in my data key. I have, here I'm saying write to the majority, and I'm having a function that tells me how I want to do that update. So, I'm using the update cart function. So I basically create the update message, and then I tell that to the local replicator, and that replicator then will, disseminate the message underneath the covers. I can also do change notification. Change data capture is actually something that you can't do very well in traditional database systems, which makes Akka distributed data really nice, is I can listen to subscriptions for changes. And I'm going to show you a quick example of this. So change notifications, right? I subscribe to a change event in Akka, and I can receive those change events. There's a whole pruning algorithm I won't go into, but basically it uses vector clocks to keep track of when a node gets removed from that distributed data cluster to figure out how to, which portions of the data to remove. All right, so I have a sample here. So I'm going to just spin up a 3-node cluster here on my laptop. Right, what I'm basically doing is I'm saying, starting Akka cluster here, I'm starting on port 2551. Let's see here. So it's started in the background. I'm going to start up on my 3-node cluster. So what this 3-node cluster is going to do is I use the shopping cart example from the Akka distributed data samples, and basically running this on a 3-node cluster. What I can do is I can do an add, which is going to add items. I randomly pick, out of a list of 4 items, which items to add. So here I added, mangoes. I added 3 mangoes to my cart. If I look at my other nodes, the other nodes are subscribing to changes, and so they've seen that I've added 3 mangoes. So that's being replicated across that cluster. So I can do an add. This time I added 2 bananas. And so you see these changes being replicated across the cluster. So let's see, I added more mangoes that time. Now I've added some oranges. And so as you see, every time I add something, these changes get replicated across the cluster. It's using this update function to keep track of how to merge these values into a single value. And then I can remove something. So let's see here. I can remove remove line item 4. Right, so it removed the mangoes from the cart. Right, and then in the other nodes, I see that remove has happened. So what this is using is it's using that replication to replicate the data across the network. Just a quick peek at the code. That's it. It's probably. This is the Scala one. I want to show you the Java one. So the key is this write consistency. This is probably too small. File. View. Enter presentation mode. So I'm specifying the write majority, right? This is the number of nodes I'm writing to. And then if I go down and I look at the shopping cart, right, this is where I'm receiving the messages. So I get a message to match an add item. So I get an add item message from Akka. This is going to add the item to my cart. What I'm going to do is I'm going to give it an update message. I'm going to create the update message, right? And then I tell the local replicator, do the update. If I look at the update cart, this is the merge function, basically. So what I'm doing for when I'm merging my shopping carts is I'm looking to see if I already have that product ID in there. If I already have it in there, I'm just going to increase the quantity. So if I get a duplication of shopping cart items, I'm just going to say, well, let's just merge it by increasing the item. The last thing just to point out is the replicator. Right, so all I'm doing to get the replicator is I'm just saying distribute data, get the replicator out of there. So I'm asking for that replicator, and then I'm going to use that to send messages across my cluster. So, all right, we'll leave is there 5 more minutes?
Yeah, 5.
5 minutes? All right, 5 minutes for questions or comments? Yeah, go ahead. The microphone.
Yeah. Can you show an example where you consume the data that is in the replicator, where you get the data?
So the Akka distributed data underneath the covers handles the replicator. Basically, I send the message to the replicator, and then it basically handles that. So then what happens is, let's see here, receive. What it's going to do is internally, that replicator will use that update cart method to resolve my local view of it. So basically, when I get an update message, I don't ever ask to manually handle that. So you notice here, I get a message for a get cart, add item, remove item, match other. So I'm never manually handling that replicator update myself. What it's doing is the replicator underneath the cover is handling that update for me. And so I only have to handle an add item, and then underneath the covers, it's going to take care of that updating the replicator state. So I never interact directly with the replicator other than saying add an item or get an item back out. So I can do like a get cart, right? So I can say I get a cart, and then I get a message back that hands me my local cart. So I never have a direct pointer to that cart. I'm just getting a message. So if I do a get, I'm just receiving a message back with the current state of the cart, but I'm never having an actual cart myself. So, yeah, go ahead.
Is there support for sharding the data?
Sharding?
Yeah, so instead of having the entire state.
Yeah. Is there sharding? How does sharding work? Do you know?
No, there is sharding, but that's a different thing.
Yeah, there's Akka sharding. I guess one thing you can do, we were kind of talking a little bit about this, like if I have a observe remove map, if I have like 1,000 items in my observe remove map, that gets to be too large, and so I want to actually break that map up into into a map of 100 items. So there's not Akka cluster sharding will automatically shard my actors. The distributed data doesn't use that cluster sharding directly, but I can do some type of manually, basically breaking up the data structures. Is that how you'd explain it best?
Yeah, but I would still say
it's a different concept, yeah. It is, Akka cluster sharding is different than, it's not directly supported by distributed data. Yeah.
Okay, thank you.
Any other questions, comments? Great. All right, thank you very much. Appreciate it.